Namaskar, welcome to the channel Anka Ananda Aharan. Today we are going to discuss about complex matrices. Before starting to discuss about complex matrix, we must know what do we mean by complex number. Some of the properties of complex number. Let Z belongs to C and let Z is equal to A plus IB. So here that implies real Z is equal to A, imaginary part of Z is equal to B, and here some properties, that is property number 1, Z bar is equal to conjugate of Z, that is equal to A minus IB. Second, Z1 plus Z2 whole bar is equal to Z1 bar plus Z2 bar. Third property, Z1 into Z2 whole bar is equal to Z1 bar into Z2 bar. These are properties of conjugates. Then what is mod Z? Mod of Z is equal to A square plus B square whole root over. So here A and B, they are the real parts of Z. Next, Z bar is equal to Z implies and implied by Z is real or imaginary part of Z is 0. Similarly, Z bar is equal to minus of Z implies and implied by Z is purely imaginary or 0. That is imaginary. That or 0. That is what? That is real part of Z is 0. That is real part of Z equal to 0. These are the meanings. Now with these conditions, let us consider complex number, vector space of defined on the field of complex numbers. Let's see n. Here the vectors belong to Cn, that means x belongs to Cn implies x is equal to x1, x2 up to xn, where xi belongs to C. Then we used to tell this. So now what about length of this vector? So such any matrix having defined on complex numbers is a complex matrix, and any vector defined on complex numbers is a complex vector. In case of complex vector, what about length of x? Is equal to length of x, that is equal to a square. So it is length of x is equal to what? Square root of I is equal to 1 to n mod of xi square. Means each component's absolute value is squared and such values are summed up, then their square root is the length. Okay, and here xh is equal to x conjugate transpose or x transpose conjugate. They are same. So as they are same, I can write they are equal to each other. Okay, now inner product ଏଇଟା ଗୋଟେ ଶବ୍ଦ, this is one word, inner product of x and y is equal to xh y. How to write it down? xhy is equal to what? Is equal to x bar t of y. X conjugate transpose into y. That is equal to how much? x1 conjugate y1 plus x2 conjugate y2 and so on xn conjugate yn. So here what is our y? Y is nothing but a complex vector y1, y2 up to yn. This is our vector y. If this is my x already we have defined. So their inner product is considered like this. Now in terms of inner product, what about length? Length of x is equal to x h x whole root over. Okay. Now here there is a simpler way to find out. Oh. Again I have to go for another vector. Just we will go for a new space. Just few seconds. So we have discussed about how to find out length and inner product of two vectors in a complex matrix space. Let us find out their value. So how to find out? It is consider x is equal to 1 plus I 2i and y is equal to I minus 1 2. Let us assume, just I have written. So here x h y, which is the inner product of x and y, x and y is equal to how much? x1 conjugate y1 plus x2 conjugate y2. That is, what's the conjugate of x1? That is 1 minus I into y1 is I minus 1 plus its conjugate minus 2i into 2. So how much it is? 1 minus I whole square. So let us find out it. How much it is? It is I, it is minus I square, it is plus I, it is minus 1 plus a minus 4i. Okay, this into this, it is minus I square, it is minus plus I minus 1. So how much it is? It is kitchen plus. So this is equal to this I plus I 2i. It is minus 1 plus 1 cancels. So it is I square means minus 1. So it is minus 1 plus 1 cancels. So plus 2i minus. So it is minus 2i. This is the inner product. Now what about length of x? Length of x is nothing but each component's coefficient square sum whole root over. That is 1 square plus 1 square plus 2 square whole root over. That is 4 plus 2 root over 6. Similarly, what about length of y? It is, how much it is? I minus 1. That is 1 minus 1 plus 1. What was the second component? 2. Oh, same value. So into 2 square. That is, it is also root over 6. So we got how to calculate length and inner product of two vectors. Now we will discuss something very significant and very important for examination point of view, that is Hermitian matrix and skew Hermitian matrix. AH is equal to A, then A is Hermitian, and AH is equal to minus of A, then A is skew Hermitian. Okay, so let us find out some examples of Hermitian and skew Hermitian matrices. So here the matrix is for Hermitian matrix. Hermitian. Here for Hermitian case, the matrix A will be, all the diagonal elements will be real, purely real. And conjugate numbers, the transpose positions, this and this, this and this, this and this, they will be conjugate of each other. That means, for example, it is 2 plus I, it is 2 minus I, it is 9 minus 3I, it is 9 plus 3I, it is, suppose how much we will do, something 6 minus 4I, it is 6 plus 4I. So this is my example of a Hermitian matrix. Here the criteria are, all the diagonal elements must be positive, must be real numbers. Extremely sorry for my wrong statement. All the diagonal elements should be real, that is their imaginary part should be 0, and all the transpose positions, they should be having same real part, opposite imaginary part. That is, they are conjugates of each other. Then it is Hermitian. Similarly, how to write down skew Hermitian matrix or verify whether a matrix is skew Hermitian or not. What we will do? Here the matrix will have either 0 or purely imaginary diagonal elements. And transpose positions, 2 plus 3I, 5 minus 7I, 2 minus root 3I. Okay, it is root 3. So in this case, the transpose position will have same imaginary part, opposite signed real part, that is minus 2 plus 3I minus 5 plus 7I minus 2 minus root 3I. This is an example of a skew Hermitian matrix. Okay. Now, unitary matrix. What do we mean by unitary matrix? This Hermitian is the generalized version of a symmetric matrix. That means if a Hermitian matrix is real, then it is symmetric. If a skew Hermitian matrix is real, then it is skew symmetric. If a unitary matrix is real, then it is orthogonal matrix. So here whatever the unitary matrix, here it is having U H U is equal to I is equal to U H. Any matrix satisfying this condition is said to be a unitary matrix. So here U inverse is nothing but U H, and it has some specific properties satisfied. If U1, U2 up to UN are n columns of U, of the unitary matrix U, then what will happen? Then UIH Uj is equal to 0 if I is not equal to j, and is equal to 1 if I is equal to j. That is, they form an orthonormal system of vectors. And few more concepts. That is, length, it is length preserving. Length of u of x is equal to length of x. How to prove it? What is the length of x? First of all, any vector's length is, so we will start with the square. Okay, let us prove it. Proof. Proof. They are important. These proofs are important. That's why I am doing. Ux h ux. Okay, so here this Hermitian property, it is, I have not told, just now I will tell. That is, it satisfies four properties. A B whole h is equal to BH, just like transpose. AH. AH H. Sorry, H is A. And A plus B whole H is equal to AH plus BH. These are the properties they satisfy. Now using this, how can we write? We have started with this is equal to what? Ux length square is equal to, this is equal to this much, which is equal to how much? Let us expand it. It is xh ux that is equal to u is identity matrix, so it is xh x, which is equal to square of length of x. Now, as norm length is always non-negative and x are non-negative, we can take the positive roots on both sides. This implies ux length is equal to x length, means unitary transformations are length preserving. This we got. Now we will prove another proof, that is, for lambda and eigenvalue of u, what will happen? Mod lambda is equal to 1. This is to be proved. Okay, let lambda be an eigenvalue of u. That implies what? That implies there exists non-zero vector x such that ux is equal to lambda x. Now, what about this lambda? So this implies length of ux is equal to length of lambda x is equal to mod of lambda into length of x, that is equal to length of x. That implies what? X, length of x is greater than 0. Already from this condition, x is non-zero means its length is always strictly greater than 0. Now, lambda into mod lambda into length of x is equal to length of x. which I can divide both sides, so that I got is equal to 1. It was to be proved, hence proved. Now we will prove that Hermitian matrices, the eigenvalues of Hermitian matrices are real. It is important again. The eigenvalues of a Hermitian matrix are real. Let us prove it. Let lambda be an eigenvalue of a Hermitian matrix A. As it is Hermitian, so that implies there exists x not equal to 0 such that Ax is equal to lambda x and Ah is equal to A. This condition is for Hermitian matrix, and this is for eigenvalue. Now let us multiply both sides. X H A X is equal to, this implies, is equal to X H lambda X. Lambda is a scalar taken outside, X H A X H X, which is equal to lambda into square of length of X. But X is non-zero. That implies this is always positive. So that implies lambda is equal to X H Ax divided by length of x whole square, as since length of x is always greater than 0, I can divide it. Any non-zero real number I can divide. So here denominator is a real number. If I prove the numerator is real, then my task is over. So to prove it, I have to find out its conjugate. Let x H A X whole H. Now this can be written as X H A X whole transpose its conjugate. But this is a matrix having one row, one column. Why? Because it is n into 1, sorry, HL, 1 into n. It is transpose is taken, na? H means conjugate transpose. So it is 1 into n, it is n into n, it is n into 1. Finally 1 into 1. So any 1 1 matrix transpose will be same as itself. So it is XH AX whole bar remains as it is. It is equation 1. Sorry, it is 1, it is 2. It is equation 2. Okay? It is equation 2. Now, let us find out the other part. XH whole of H. Let us apply the Hermitian property. That is, it is XH XH whole H. That is equal to XH AH is equal to A. This is, so here two conditions we have applied. XH is equal to X, AH is equal to A. This is since Hermitian. Because of Hermitian this happens, and it is general property of Hermitian condition. So now what we got? It is equation 3. So from equation 2 and 3, left hand sides of both the equations are same. That implies XHAX whole bar is equal to XHAX. It is from 2 and 3. So z bar is equal to z implies z is real. Z is real. So that implies lambda is a ratio. Lambda is a ratio of two real numbers, which implies lambda is real. Hence proved. It is for Hermitian matrix we have proved. Now for skew Hermitian, where I have to change the skew Hermitian case, the eigenvalues are either 0 or purely imaginary. Either 0 or purely imaginary. So if here it will be written skew, here it will be written either 0 or purely imaginary. Now here instead of a there will be minus a. Okay. So in that case, rest all thing will continue as it is. Here there will be a small change, that is here it is minus, so it is minus, so it is minus. Now z bar is equal to minus of z implies it is either 0 or purely imaginary. Denominator is real and numerator is 0 or purely imaginary. Hence lambda is 0 or purely imaginary. So like this one can prove very comfortably for skew Hermitian matrices. Okay, you write it again simply, correctly for skew Hermitian matrices. What you will do? Here you will write skew Hermitian matrix. Here you will write 0 or purely imaginary. Then here you will write minus symbol. Then everything else will continue as it is. Finally, here there will be minus a. Here it is. AH is equal to A. Here there will be minus A and here there will be minus A and this here there will be minus A. So that minus will come here as minus. So z bar is equal to minus of z. Hence z is either 0 or purely imaginary. Like this we will do. Okay. So write it once again neatly. It is important. So with this, our some of the aspects of complex matrices are over. Thank you for your patience listening. In the next class, we will finish our applied algebra videos in one video. Thank you.